Welcome to Metabolomics Decoded, a concise tour through biochemical pathways and their practical impact. In this presentation, we'll explore how metabolite profiling drives biomarker discovery, connects systems biology layers, and yields therapeutic insights. Think of this as a roadmap. We'll start with fundamentals, move through analytical and computational workflows, and finish with real-world applications that bridge research to clinical and agricultural use. This slide explains why metabolomics is such a powerful readout. It sits downstream of genomics, transcriptomics, and proteomics, and captures the actual metabolic state shaped by genes, enzyme kinetics, and environmental inputs. Metabolite snapshots respond rapidly to stimuli, so they reflect physiology, nutrition, and disease in a way that upstream omics can't, making metabolomics uniquely informative for functional phenotype insights. Mass spectrometry is the workhorse of metabolomics, combining ionization methods like electrospray, or APCE, with analyzers such as triple quadrupole, Orbitrap, and TOF. Each choice trades off resolution, mass accuracy, and scan speed. And MS fragmentation provides structural clues. Robust quantification depends on matrix-matched calibration and internal standards to correct for variability and ensure reliable, reproducible measurements across experiments. Before mass spectrometry, we separate metabolites using liquid chromatography strategies like reversed phase, Heilig, or ion pairing. And for volatile compounds, we use derivatization, followed by gas chromatography. Good separation boosts peak capacity and retention time reproducibility, while orthogonal approaches reduce ion suppression and increase coverage across diverse chemical classes, giving a more comprehensive and reliable snapshot of the metabolome. NMR spectroscopy offers non-destructive profiling and definitive structural confirmation through chemical shifts and coupling constants, using proton and carbon-13 information. Advanced techniques like solvent suppression and 2D correlation help resolve overlap. And although NMR has lower sensitivity than MS, its strengths are superior reproducibility and absolute quantitation, making it ideal for untargeted analysis and validation of key metabolites. Proper sample preparation is essential. Quenching stops enzymatic activity, using rapid freezing or cold methanol to preserve metabolite levels, and liquid-liquid extraction separates polar and lipid fractions for targeted analysis. Standardization, uniform tissue homogenization, consistent sampling windows, accurate biomass recording, and 80-digit storage minimizes pre-analytical variation and protects data integrity before any analytical run. The data pipeline begins with peak processing, peak picking, deconvolution, and retention time alignment using open source or vendor tools. Metabolite annotation combines accurate mass with fragmentation spectra and public libraries, followed by normalization and isotopic corrections. Finally, quality control and batch effect removal are critical to ensure reproducible, comparable results, and to make downstream statistical and biological interpretations trustworthy. Quantitative metabolomics relies on targeted approaches like SRM on triple quadrupoles for ultra-high sensitivity and precise limits of quantification. Stable isotope-labeled internal standards normalize variability, while multiplexing enables hundreds of metabolites per run. Validation focuses on linearity, precision with low CVs, and recovery. And these rigorous parameters are what allow translation into clinical biomarker panels and therapeutic drug monitoring applications. The typical workflow moves from data acquisition, choosing DDA or DIA, to statistical analysis and pathway mapping. Differential testing with FDR control identifies significant features, and enrichment maps altered biochemical modules. Identification and validation require follow-up with MS and independent cohorts, because confirmation with orthogonal methods is mandatory before making biological conclusions or Biomarker claims. Translating metabolomics into clinical practice follows clear phases: discovery, cohort profiling, replication across populations, establishing biological plausibility, and technical assay transfer optimized for clinical labs. Regulatory validation with CLIA or FDA standards comes next. And finally, integration into electronic health records for stratified care. Each phase ensures that initial findings evolve into validated, usable diagnostics or therapeutic decision tools. In crop improvement, untargeted metabolomics can profile, segregating populations to locate QTLs linked to flavonoid and sugar content, producing heat maps and trait associations. Metabolic genome-wide association studies then link SNPs to pathway intermediates, and marker-assisted genomic selection uses those insights to accelerate breeding of nutrient-enriched, stress-resilient crop varieties, improving selection models and breeding efficiency. Microfluidic sweat analysis pairs tiny channels and sensor arrays for colorimetric and electrochemical readouts of lactate, glucose, and drug levels, enabling continuous monitoring through Bluetooth-enabled apps. Major challenges include calibration drift and inter-individual variability, but the closed-loop vision is compelling. Automated analysis feeds personalized nutrition or pharmacological interventions, creating real-time feedback systems for individualized health management.